Walk into any gym and you will see two very different approaches to moving weight. On one side, lifters drive the barbell explosively. On the other, they grind through the repetition with agonizing slowness, carefully eliminating all momentum. The fitness industry has a name for this slower method: time under tension. The prevailing assumption is that by moving the weight slowly, you directly increase the mechanical tension placed on the muscle fibers. Because of this assumption, lifting with momentum is frequently vilified. It is written off as dangerous ego lifting, a way to cheat the movement and escape the hard work. But if we analyze a standard free weight lift through the strict lens of classical physics, a major mechanical flaw in this philosophy emerges. Equating a slower movement speed with higher muscular tension is a complete misunderstanding of how the human neuromuscular system produces force in the real world.
To understand what actually happens when you lift a weight, we have to treat resistance training as a mechanical engineering problem. We are dealing with mass, acceleration, and geometric force vectors. The primary physical challenge of any free weight exercise is the simple act of overcoming static equilibrium. Classical physics defines the force a lifter exerts with an equation: force equals mass times gravity plus mass times acceleration. The first component, mass times gravity, represents the baseline force required to hold the mass motionless. The second component, mass times acceleration, represents dynamic force. This is the extra effort required to accelerate that mass upward. When applied over time, it produces a propulsive impulse, which is exactly what generates momentum. Momentum, then, is not a failure of lifting technique. It is the mathematical byproduct of a neuromuscular system successfully applying propulsive force to an object. We can see this mechanical reality in the data. In 2008, biomechanist Brian Schilling and his team conducted a case study using a force plate to measure the output of an 85-kilogram athlete performing back squats. The study compared mechanical output of two distinct lifting styles: a normal speed repetition with maximal acceleration, and a purposefully slow repetition featuring a 10-second concentric phase. In both conditions, the mass of the loaded barbell remained absolutely constant. The baseline static weight was exactly the same for both lifts, with upward muscular force perfectly balancing gravity. To initiate movement, the applied upward force must mathematically exceed gravity. The difference between these vectors over time constitutes the propulsive impulse that creates velocity. By definition, any intentional reduction in velocity mathematically demands a corresponding reduction in applied propulsive force. This chart shows force plate data during the normal maximal acceleration squat. Notice where the force curve spikes dramatically upward. This spike represents the propulsive impulse required to accelerate the barbell. Below, we see the resulting increase in bar speed. That initial spike in force generation is the result of the lifter's central nervous system achieving a state of maximal voluntary muscle activation. Even if a heavily loaded barbell is physically moving slowly, the neurological intent to accelerate it must remain at absolute maximum to generate that force. Standard lifting speeds produce massive peaks in mechanical force, specifically because the lifter intends to accelerate the load. Compare that to this chart showing the purposefully slow 10-second squat. The force curve is essentially a flat line, barely rising above the dotted line representing the barbell's static weight. By deliberately suppressing acceleration, the lifter causes the propulsive impulse to drop to near zero. This exposes the paradox of the purposefully slow method. Time under tension increased by 400%, but the peak and mean propulsive forces applied by the muscles were drastically lower. This matters because of the size principle of motor unit recruitment. Small, slow-twitch motor units activate first at low force levels. The larger, fast-twitch muscle fibers, which have the highest capacity for strength and hypertrophy, are only recruited when force demands cross a high threshold. Intentionally eliminating acceleration keeps the lifter's total force output trapped below that critical activation threshold. The purposefully slow training style burns more energy over a longer duration, but it fails to provide mechanical tension necessary to recruit high-threshold motor units for tissue adaptation. If acceleration produces the most force, we must ask if the data supports the other extreme. Is maximum uncontrolled momentum, typically called ego lifting, universally optimal? The short answer is no. There are severe biomechanical risks associated with wildly jerking the weight to create rapid acceleration. Excessive momentum shifts the peak external torque away from the target muscle tissue, transferring that dangerous load directly onto passive structures like tendons and joints. Wild acceleration also creates a pendulum effect. The lifter ends up skipping the critical extremes of a joint's range of motion entirely. This illustrates why that matters. Emerging research points to training muscles at long lengths, when they are fully stretched, as a primary driver of hypertrophy. Exposing a muscle to high external torque in a maximally stretched position triggers specialized mechanical signaling for muscle growth. Momentum crosses the line into dangerous ego lifting when it removes torque from the target muscle precisely at its most stretched and vulnerable position. However, recent biomechanical literature defends a more nuanced approach, the strategic, controlled use of momentum during resistance training. Applying slight, deliberate external momentum can actually help a lifter push past mechanically disadvantageous sticking points in a range of motion. Bypassing those specific weak points allows the lifter to spend more total time applying high internal force precisely at those critical long muscle lengths. There is a strict difference between passive time under tension, achieved by moving light weight slowly, and active mechanical overload, achieved by exerting heavy, intentional force. The ideal mechanical environment for muscle adaptation involves a specific sequence, a controlled eccentric yielding phase, immediately followed by maximal concentric acceleration intent. This specific movement pattern balances structural safety with the high propulsive impulse physically required to recruit fast-twitch fibers. Momentum isn't a biomechanical error. It is an essential physical requirement for generating the mechanical tension that drives maximum strength and tissue adaptation.